Swayam Prabha. Digital India. Educated India.
So, in earlier lectures, we have discussed different methods for the model fitting and forecasting of different stationary time series processes. What is left after the fitting the model is the model residuals. Usually, the residuals are the difference between actual values of the time series observation and the corresponding predicted value. These residuals must satisfy some properties. If your model fitting is good and if your model is able to forecast the future values of y properly, then these residuals, this leftover must satisfy certain properties. Some of the properties are, say, these residuals should have 0 mean, constant variance, and then one important property is these residuals are mutually uncorrelated with each other. So, if you calculate the auto correlation function for these residuals, then autocorrelation function should be approximately, at least approximately equal to 0. If these residuals are not uncorrelated, then what does it mean? It means that these residuals still have some information which can be further utilized to improve the forecasts, or your model requires some improvement. You must look at the model again and you must revise your model. And another property of these residuals which you require in many testing problems is that these residuals should be normally distributed. So, before proceeding ahead, we must check these properties of the residuals. We fit the model, we calculate the residuals, and then we check whether these residuals satisfy all these properties or not. So, for that purpose, we use different diagnostic checking methods. So, in this lecture, we consider different diagnostic checking methods for stationary processes. So, basically these diagnostic tests are primary tools for model diagnostic checking in residual analysis. And then in these tests, we test for serial uncorrelatedness, and for that purpose, we use well known Q tests. Now, if a time series is serially uncorrelated, then no linear function of the lagged variables can account for the behavior of the current variable. And if your residuals are correlated, it means still some information has been left over which can be utilized to improve your model and improve your forecasts. Then we can apply tests to check if the estimated residuals follow a white noise process or not. Now, suppose you have fitted an ARMA PQ process. Then we define the residuals as say W hat t equal to y t is the observed value minus y hat t phi hat theta hat. This is the predicted value of y t, and theta hat and phi hat, these are the estimators of the parameters theta and phi. these may be least square estimators or maximum likelihood estimators, and then we divide it by r t minus 1 phi hat theta hat to the power half, and then W hat t is actually the scaled residual of fitted ALMA PQ process. Sometimes we also use rescaled residuals, which are denoted by R hat t, and in R hat t we divide W hat t by 1 upon n summation t equal to 1 to n W hat t square to the power half. So, actually if mean of these residuals W hat t is 0, then this gives you the standard deviation of the residuals. Y hat t, phi hat, theta hat is the predicted value of y t, and y hat t, phi hat, phi hat and theta hat, and r t minus 1 phi hat theta hat can be obtained using the innovation algorithm, which we have discussed in the last lecture. Now, if you have fitted a proper model, a true model, means if your fitted model is the true ALMA PQ model, then the estimated residuals should behave like a white noise process. So, this is something in which we are interested, whether your estimated residuals follow white noise process or not. And what are the properties of white noise process? Different terms are uncorrelated. So, W hat t converges to the white noise process U t generating ALMA PQ process, provided these estimated residuals are from the true ALMA PQ process. Means you have fitted ALMA PQ process, which is the actual process from which you have generated the data, and then these are the residuals. Then another choice of estimated residuals is U hat t equal to theta hat b inverse phi hat b y t, where these theta hat b and phi hat b are polynomials of ALMA PQ process. The only difference is that we have replaced the thetas and phis by their corresponding estimators. So, W hat t is the sequence of estimated residuals, and then sample ACF of W hat t is defined as, say, rho hat W k equal to summation t equal to 1 to n minus k, W hat t minus W bar, W hat t plus k minus W bar divided by summation t equal to 1 to n minus k, W hat t minus W bar square, for all k equal to 1 to so on. So, you may define the ACF of these estimated residuals like this. And if your process W hat t is a white noise process, then these rho hat W k should be insignificant or close to 0 for all k equal to 1 to so on. Now, first we consider some graphical techniques for model validation. For that purpose, we consider these 4 graphs. These 4 graphs are the primary tools for model diagnostic checking in residual analysis. The first graph is run sequence plot. The run sequence plot, this plot of estimated rescaled residuals against time indicates if the residuals follow the assumption of constant location and scale or not. So, if we plot W hat t against t, then by looking at that graph you can say that whether the mean of the estimated residuals is 0 or not, and whether the variance is constant or not. The second plot is lag plot. A lag plot is a plot of W hat t against, say, h period lagged estimated residuals W hat t minus h. So, on x axis we take w hat t minus h, on y axis we take w hat t. Usually we take h equal to 1. So, we plot w hat t minus 1 against w hat t, and if you take h equal to 1, then on x axis you are taking w hat t minus 1, and on y axis you are taking w hat t. By looking at lag plot, you can identify whether your residuals are randomly distributed or not. Then the third plot is autocorrelation plot of the residuals. So, you fit your ARMA PQ process, calculate the residuals W's, and then you plot the ACF of the residuals. And by looking at the ACF, you can say whether your residuals follow white noise process or the residuals follow AR1 process or MA1 process. So, if the residuals follow AR1 process or MA1 process, then this implies that still some information is left over there, and you must redefine your model. Fourth plot is histogram and normal probability plot. This indicates that the normal distribution provides an adequate fit for the model or not. So, here I have given a simple example. We have simulated a sample of size 10,000 from the AR1 process, yt equal to 0.6, yt minus 1 plus ut, and then we have fitted AR1 model. And since we are fitting correct model, then your estimated residual should behave like a purely random process. So, then we have calculated the residuals, and then we have plotted the residuals using run sequence plot. So, on x axis we have taken time, on y axis we have taken the residuals. So, we get this kind of graph. And by looking at this graph, you can easily identify that the mean of the process is 0 and the residuals have constant variance. So, you get some idea about the mean of the residuals and their variances just by looking at this graph. Next, we consider the lag plots. Lag plots can provide answers to these questions. Say, are the estimated residuals random? Is there any serial correlation in the residuals? What is a suitable model for the data, and are there outliers in the data? Now, we have plotted the residuals for the same simulated data set. We have drawn sample from the AR1 process, then we have fitted AR1 process, then these are the residuals lag plot. So, you can easily say that these residuals are distributed randomly. In case you observe some kind of pattern, so suppose your graph is something like this, or somewhat like this, then you cannot say that your residuals are distributed randomly. These residuals show some kind of pattern. But here in this graph, these residuals show no pattern. These residuals are just randomly distributed. So, you can say that these estimated residuals are just follow purely random process. So, using this lag plot, it checks whether W hat T are random or not. Random residuals should not exhibit any identifiable structure in the lag plot. You should not have any trend in the lag plot or any identifiable structure it should not show. Means if all the lag residual points are distributed around a straight line or around any particular curve, then you cannot say that your residuals are randomly distributed. So, any non-random structure indicates that the estimated residuals are non-random. Then you have to look at your model again. You have to restructure your model or re-specify your model. Another plot is ACF and PACF plot. Not only ACF, you can also look at the PACF plot. So, we take the residuals as a time series and then we obtain the ACF of the residuals and then we plot the ACFs or we plot the PACF both. Now, for our example, both ACF and PACF are insignificant. These ACF and PACF look like the ACF and PACF of a purely random process. So, you can say that these residuals follow purely random process or your fitted model is appropriate. You have fitted an appropriate model, a true model. And this is actually what we have done. We have generated data from AR1 model and then we have fitted AR1 model. So, obviously, our fitted model is the true model. That is why we are getting so nice results. Our lag plot is just like the plot of purely random process. There is no pattern. If we plot ACF and PACF, then we get all the insignificant values of ACF and PACF. So, the reason is very simple, because we are able to select the proper model. But suppose you generate data from ALMA 1.1 model and you fit AR1 model, then your residuals may look like, or if you plot the ACF and PACF of your residuals, it may look like the residuals of some MA process, or it may show these residuals may show some kind of autocorrelation. So, then you look at your model again and then you specify your model again. These are the histogram and normal QQ plot for your residuals. I will come to these normal QQ plots again in detail. I will discuss these normal QQ plots in detail, but just looking at this histogram, you can easily say that the distribution of these estimated residuals is normal. This graph looks like the graph of a normal distribution. So, your residuals follow normal distribution. In fact, while generating data, we have drawn residuals from a normal distribution. That is why you are getting this kind of graph. And this is the normal QQ plot, which I will explain later on. Now, we consider some tests for serial uncorrelatedness. So, basically you are interested in checking whether WHT are serially uncorrelated, and these WHT are serially uncorrelated means its ACF is identically 0. So, for all values of k, rho hat W k is equal to 0. So, your null hypothesis is for a given number m, you just take this number m, which is the maximum number of autocorrelations which you are going to consider for testing the significance. So, for given m, your H naught is rho 1 is equal to rho 2, so on equal to rho m equal to 0. So, all these m autocorrelations are insignificant equal to 0. This is the hypothesis in which you are interested. And then we estimate the sample autocovariances for W hat t by C k equal to 1 upon n summation t W hat t minus W bar, W hat t minus k minus W bar. W bar is the mean of these estimated residuals, and then rho hat k is the sample autocorrelation for W hat t, and rho hat k is equal to C k upon C 0. So, this is the kth sample autocorrelation. Now, suppose you write rho m equal to the vector rho 1, rho 2, rho m. So, this is actually m cross 1 vector, and the corresponding vector of estimated autocorrelations is rho hat m, which is equal to rho 1 hat, rho 2 hat, so on rho m hat transpose. Then under very general conditions, as n tends to infinity, under root n rho hat m minus rho m follows normal distribution with mean 0 and variance covariance matrix V. And the ijth element of V matrix is given by V I j equal to this. Well, I have not given here the details of the proof of this result, but this result plays an important role in obtaining the test for the significance of all these autocorrelations rho 1, rho 2, rho m. Now, suppose all these rho k's are equal to 0 except rho 0, then you have to obtain the value of V I j. Okay. Then as n tends to infinity, rho hat m minus rho m transpose V inverse rho hat m minus rho m follows a chi-square distribution with m minus p minus q degrees of freedoms. In fact, if you look at this slide, then if x follows a multivariate normal distribution with mean vector mu and variance covariance matrix sigma, and x is p cross 1 vector, then x minus mu transpose sigma inverse x minus mu. This follows a chi-square distribution with p degrees of freedoms. Now, here under root n rho hat m minus rho m follows normal distribution with mean 0 and variance covariance matrix V. Then rho hat m minus rho m transpose V inverse rho hat m minus rho m. This follows a chi-square distribution, and the degree of freedom is m minus p minus q. So, we have reduced the degree of freedom by p plus q, and the reason is because you have p plus q parameters, phi's and theta's, and you have estimated those parameters also. So, you have reduced the degree of freedom by p plus q. Under H naught, when all the y t's are serially independent, then you can easily verify that V I plus 1 j plus 1 is equal to 1 if I is equal to j, and it is 0 if I is not equal to j. And this also you can easily verify from the previous expression for V I j. So, suppose I is equal to j, then here you get for I equal to j rho k square. Under H naught, all the rho k's are equal to 0 except for k equal to 0, and for k equal to 0, rho k square is equal to 1. Then in second expression, rho k plus j, rho k minus I, for I equal to j, either rho k plus j is equal to 0 or rho k minus I is equal to 0, or both are equal to 0. So, this expression is, this term is equal to 0. Similarly, you look at the third term, rho j, rho k minus I. So, for I equal to j, you will not find any term which is not equal to 0. Here also, this term is equal to 0, and this term is also equal to 0, even for I equal to j. And for I not equal to j, even this term is equal to 0 for all values of k when I is not equal to j. Because if you take k equal to 0, then rho, here you get rho 0, but here you get rho k minus I plus j, and since I is not equal to j, so this term is not equal to 0. So, finally, you obtain V I plus 1 j plus 1 equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. So, V is equal to I under H naught, and basically in testing of hypothesis you are interested in the test statistic, distribution of the test statistic under H naught. So, for residuals of alpha PQ process, as n tends to infinity, the distribution of V denoted by Q B P n equal to n rho hat m transpose rho hat m equal to n times, and then this product is equal to summation j equal to 1 to m rho hat j square. This follows the chi-square distribution with m minus p minus q degrees of freedoms, and this statistic is the well known box Peirce Q statistic, and you can use this statistic for testing the hypothesis that all the autocorrelations rho 1, rho 2, rho m are equal to 0. If this statistic, you compare this statistic with the tabulated value, and if this is greater than the tabulated value at say 5% level of significance, then you reject the null hypothesis. You say that your test indicates that the estimated residuals are not random or not follow purely random process, and you accept the null hypothesis, then you say that your residuals follow purely random process and they are uncorrelated. Now, this is a Young box modified Q test when W hat T's are independently distributed random variables with mean 0 and finite variance and finite sixth moment. So, you require this assumption also about the sixth moment, it has finite sixth moment. Then the covariance between rho hat I and rho hat j is approximately equal to n minus I upon n plus the terms of order O n inverse if I is equal to j, not equal to 0, and this is equal to a term of order O n inverse if I is not equal to j. So, for I equal to j means variance of rho I head is approximately equal to n minus I upon n, and I not equal to j means covariances are equal to 0. So, under H naught you have this result, because under H naught W hat T's are independently distributed random variables. Now, this leads to modified Q test of Young and Box. Now, your matrix V is different. In the diagonal you have elements n minus 1 by n, n minus 2 by n, and so on, n minus m by n. Now, this leads to the modified Q test of Young and Box. So, Q L B is equal to n square summation j equal to 1 to m rho hat j square upon n minus I. Now, we consider Young Box modified Q test. So, when W hat T's are independently distributed random variables with mean 0 and finite variance with finite sixth moments also. So, you require this additional assumption, W hat T's have finite sixth moment, and independently distributed means rho 1 is equal to rho 2 equal to so on rho m equal to 0. So, under these conditions, covariance between rho hat I and rho hat j is approximately equal to n minus I upon n plus terms of order n inverse if I is equal to j, not equal to 0, and this covariance is approximately of order n inverse if I is not equal to j. Again, I have not given here the detailed derivation of this result, but it means that these rho hat i's are uncorrelated at least up to order O n inverse, and their variance is equal to n minus I upon n. The variance of rho hat I is n minus I upon n. So, the diagonal elements of matrix V are now n minus 1 upon n, n minus 2 upon n, and so on. Then if you consider the statistic, rho hat m transpose V inverse rho hat m, then since V is a diagonal matrix and these are the diagonal elements of V, its inverse elements are n upon n minus 1, n upon n minus 2, and so on. So, ultimately you find this modified Young box statistic as n square summation j equal to 1 to m rho hat j square divided by n minus j. One n was already there, you have n also here, and then you get 1 n from here, you get n square then, and then you are dividing by n minus j here, and this follows a chi-square distribution m minus p minus q as n tends to infinity. So, again you can form a test for testing the hypothesis H naught that rho 1 is equal to rho 2 equal to so on rho m equal to 0 using this statistic, the modified Q test, Q statistic. If this calculated value is greater than the tabulated value, then we reject the null hypothesis, and then we say that your estimated residuals do not follow white noise or purely random process. So, you must look at your model again, and if this hypothesis is accepted, then you say that your residuals follow purely random process. These residuals are at least uncorrelated. Then this Young-Box Q statistic is also computed as in this form. Instead of taking n square, we take n into n plus 2. So, this is another version of Young-Box Q statistic. Then another modified version of Q statistic is Q star equal to n summation j equal to 1 to m rho hat j square upon v hat j j, where you obtain v hat I as 1 upon n summation t equal to 1 to n minus I w hat t minus w bar square w hat t plus 1 minus w bar square divided by 1 by n summation t equal to 1 to n minus I w hat t minus w bar square whole square. This also follows chi-square distribution with n minus p minus q degrees of freedoms. So, using this statistic also you can test the hypothesis that all the autocorrelations are insignificant, rho 1, rho 2, rho m are insignificant. Now, sometimes what happens, your residuals are uncorrelated, but squared residuals are not uncorrelated. So, you can test this hypothesis of squared residuals for correlation. So, suppose you define rho hat w w k as the sample ACF of squared residuals, which is equal to summation t equal to 1 to n minus k w t hat square minus w bar square w hat t plus k square minus w bar square upon summation t w hat t square minus w bar square. So, this is actually the sample ACF for squared residuals. Here do not confuse this w bar square with the square of w bar. Actually, this w bar square is the mean of w t squares. So, this w bar square is equal to 1 upon n summation t equal to 1 to n w hat t square. Then as n tends to infinity, the statistic q w w n n plus 2 summation k equal to 1 to m rho hat square w w k upon n minus k follows chi-square distribution with m degrees of freedoms. So, you can check using this statistic whether your squared residuals are uncorrelated or not, and we reject H naught at level alpha when this calculated statistic is greater than the tabulated one. Now, we consider some tests for randomness. If your estimated residuals follow purely random process, then those residuals must be randomly distributed. And to test whether those residuals are randomly distributed or not, now we consider some non-parametric tests. The first test is based on the turning points. Now, how we define a turning point? If w hat t is greater than both w hat t minus 1 and w hat t plus 1, means this is your w hat t and this point is w hat t minus 1 and this point is w hat say t plus 1. So, it is greater than both, then this is a turning point. The second possibility is your w hat t is less than both w hat t minus 1 and w hat t plus 1. This is say w hat t, this is w hat t minus 1, w hat t and w hat t plus 1. So, again this is a turning point. So, if any of these two conditions is satisfied, then for t equal to 2 to n minus 1, the corresponding point is a turning point. Now, suppose capital T is the total number of turning points. Then, if w hat t for t equal to 1 to n are IID random variables, then t is a turning point with probability 2 upon 3. And in that case, expected value of t is equal to, say we denote it by mu t, 2 into n minus 1 upon 3. And variance of t is equal to 16 n minus 29 upon 90. So, if t minus mu t is large, it means the series is fluctuating more rapidly than the usual random series. Look, this mean you have obtained under the assumption that WTs are randomly distributed. If WTs are randomly distributed, if these are IIDs, then expected value of number of turning points is 2 n minus 1 upon 3. And if number of turning points is larger than mu t, then this is an indication that the series is fluctuating much more rapidly than the usual random series, and it means that the neighboring terms have negative correlation. Negative correlation, why? It is fluctuating more rapidly between plus means for the usual random series, of course, you will get some fluctuations, but for this series, since you are getting more fluctuations, means you have more turning points. So, this is an indication that the terms are negatively correlated, and if W t is below the point W t minus 1, then there is a high probability that W t plus 1 is above the point W t. So, you get a lot of fluctuations, and this is an indication of negative correlation. A small value of t minus mu t, this is an indication that your terms of W t series are positively correlated among neighboring terms. Now, you can apply this logic for the testing the randomness of the series. For IID sequence, if you take the statistic z equal to t minus mu t upon sigma t, this follows normal 0 1. and we reject the hypothesis of random sequence at 100 alpha % level of significance if mod of z is greater than capital phi 1 minus alpha by 2. Here capital phi 1 minus alpha by 2 is 100, 1 minus alpha by 2 percentage value of normal 0 1. So, you can easily obtain this value from the normal table, from the CDF of normal table. Say suppose you take 5% level of significance, then this value phi 1 minus alpha by 2 is equal to 5.975. So, you take the value 5.975 here. If mod value of z is greater than that tabulated value, then you reject the hypothesis that your random sequence, though your sequence is random. The second test is difference sign test. Now, you consider the differences w hat t minus w hat t minus 1, and then we count the number of values of t for which this difference is positive. So, we only consider those values of t for which these differences are positive for t equal to 2 to n, and then we count the number of such values, and suppose s is the number of points or number of such points. Now, under the random sequence assumption, expectation of s is equal to half n minus 1 and variance of s is n plus 1 by 12. Again, a large value of s minus mu s, where mu s is the mean of s in magnitude, indicates the presence of increasing or decreasing trend in estimated white noise. So, again we consider this statistic z equal to s minus mu s upon sigma s, and for large n this follows normal 0 1, and then you can easily form the critical region for testing the hypothesis that your WTs are follow random sequence, or the WTs are randomly distributed. So, this is the critical region. The next one is rank test. Suppose P is the number of pairs H t such that W hat t is greater than W hat H for all t greater than H and H equal to 1 to n minus 1. Then finally, you have actually NC2 pairs of H t's with t greater than H, and for each pair the probability that W hat t is greater than W hat H is 1 by 2. So, expected value, suppose P is the number of such pairs, then expected value of P is equal to mu P equal to n into n minus 1 by 4. You multiply it by the corresponding probability 1 by 2, and variance of P is equal to n into n minus 1 into 2 n plus 5 by 8. Again, for large n, if you consider the statistic z equal to P minus mu P upon sigma P, this follows a normal distribution, and we reject the assumption of randomness at 100 alpha % level of significance if mod of z is greater than phi 1 minus alpha by 2. So, just like the previous tests. Now, we consider QQ plot for checking the normality. So, suppose we arrange all the time series observations in increasing order. So, this is the order statistic of a random sample from normal mu sigma square, and suppose x 1, x 2, x n is the order statistic from normal 0 1. Now, actually this is a order statistic from normal mu sigma square if and only if you have taken observations from the normal distribution. then expected value of y j is equal to mu plus sigma m j, where m j is equal to expected value of x j. Now, this is the basis for QQ plot. Expected value of y j is a linear function of expected value of x j. So, what we do? We plot m i's and y i's, and then on x axis you are taking m i's, on y axis you are taking y i's, and if you get approximately a straight line here, then you can say that your observations are from a normal distribution. You can also calculate R square, squared correlation coefficient between m I and y I. A small value of R square indicates rejection of normality assumption, and if it is close to 1, then you can say that your series follows normal distribution. For residuals, you simply replace these y j's by w hat j's, the order statistics for the estimated residuals. Again, this is the value of R square for the estimated residuals. So, the plot of phi inverse j minus 0.5 upon n and w hat j is called the QQ plot. And if your observations are from or residuals are from the normal distribution, then QQ plot looks like this. All the points are on a straight line. Now, if the QQ plot or if the residuals are from gamma distribution, the distribution is right skewed and you get this kind of QQ plot. Or if the residuals are from T distribution, then you get this kind of QQ plot. So, this is how you can identify the distribution of residuals on the basis of QQ plot. So, this is one more option. You can look at the form of the QQ plot just to identify whether your residuals are normally distributed or not. So, in this lecture, we have considered different diagnostic tests for checking whether the residuals are autocorrelated or not, or whether the residuals follow normal distribution or not. And if your model fit is good and you are fitting a correct model, then your residuals must not show any kind of autocorrelation structure. And if your residuals are showing some kind of autocorrelation structure, it implies that the residuals still have some information which can be utilized for improving your model and for improving your predictions. So, after fitting the model, before proceeding further or before finalizing the model, you must look at these tests. So, now here I am going to stop. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I'm not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I'm also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets. Hello and welcome to this piece of Literary Snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I'm not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I'm also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.